In this course, you'll get acquainted with an approach to reverse engineering using KOMPAS-3D. You'll learn which tools KOMPAS-3D provides for restoring a precise model based on a scanned model. To do this, we'll open the scanned impeller model in KOMPAS and approximate its elements, allowing us to snap to them and create elements of the precise impeller model. We'll control the approximation using the analysis tool. Finally, we'll refine the model by adding standard elements such as chamfers and fillets. If you'd like to practice, you can download a model, such as an impeller or another component, in STL or OBJ format from the internet. Websites like grabcad.com offer a large library of free models contributed by engineers and designers around the world. In the first lesson, we'll go over some key definitions related to reverse engineering. Reverse engineering is the act of dismantling an object to see how it works. It's done primarily to analyze and gain knowledge about the way something works, but it's often used to duplicate or enhance the object. The purpose of reverse engineering is to find out how an object or system works. There are a variety of reasons to do this. Reverse engineering helps recreate critical parts when original documentation is missing or the manufacturer no longer exists. By understanding existing designs, engineers can optimize for weight, durability, cost, or performance. Engineers dissect failed components to find root causes and prevent future breakdowns. Physical parts can be converted into digital models for simulation, modification, or 3D printing. In most cases, CAD systems represent geometry in two ways: using B-reps or using meshes. B-rep is a short name given for boundary representation. It represents surfaces through mathematical equations and a set of limits in 3D space. B-rep allows you to precisely define a 3D body. That is, when you model something in KOMPAS-3D, you're working with a B-rep definition under the hood. However, B-rep is compute-intensive and it's not always available. For instance, in reverse engineering workflows such as 3D scanning. Even though the model is stored as a B-rep internally, what you see on the screen is typically a visual approximation. And that's where meshes come in. Rendering engines convert B-rep geometry into triangular meshes for display. A mesh is a collection of vertices, edges, and faces that define the shape of a 3D object. Most commonly, these faces are triangles or quadrilaterals, in short quads. Mesh formats like STL or OBJ are used to export models for additive manufacturing. In finite element analysis or computational fluid dynamics, meshes break down complex geometry into smaller elements for stress, head, or flow calculations. Meshes are used in animation and game development. 3D scanners generate point clouds that are converted into meshes. A point cloud is another way of representing a 3D model. It's a collection of data points in space. These points are typically generated by 3D scanning technologies. Each point in the cloud has coordinates x, y, z, and may also include other attributes like color or intensity. Point clouds can also be used to generate 3D CAD models for analysis and manufacturing. KOMPAS-3D allows you to work with point clouds in some cases, which we will talk about later.